Welcome back to the deep dive. Today, we're really getting into the weeds, looking at how quantum mechanics actually explains stuff, like solid materials.
Yes, specifically, we're tackling a chapter from Feynman's lectures, Vol.3. It's called Propagation in a Crystal Lattice.
Right, and our mission really is to figure out how Feynman explains this big puzzle, electrons moving through solids.
It seems totally wrong at first glance, doesn't it?
Yeah, I mean, the atoms are packed super tight, right? Angstroms apart.
Exactly. Like shoulder to shoulder, classically, you'd think an electron would just bang, hit an atom immediately. No conductivity.
So it's not like a pinball bouncing around in there. How does it work then? How does it get from atom A to atom B?
Well, that's the quantum magic, isn't it? The electron acts like a wave. It doesn't really jump. It sort of leaks. It tunnels quantum mechanically from one atom to the
It
next.
leaks like water through a crack.
Kind of. Feynman uses the analogy of coupled oscillators,
Mm.
where energy just passes smoothly down a line. Here, it's the electron's probability amplitude that propagates.
Okay. So, to understand this, Feynman simplifies things a lot.
He does. He starts with just one dimension. Imagine a straight line of identical atoms, all equally spaced. A 1D crystal.
And we need a way to describe the electron's state.
Right. We use an amplitude, let's call it C$. It basically tells you the amplitude of finding the electron at atom number and along that line.
Got it. And the core rule here is this leaking idea.
That's the key. The amplitude Zala isn't stuck. It constantly leaks or tunnels to its immediate neighbors, seeing a leak and say atom +1.
And there's a specific rate for this leaking.
Yeah, there's a constant amplitude. Feynman calls it I bar per unit time, basically a measure of how easily it jumps one step. Let's just focus on the A part, that's the tunneling strength.
Okay, so this A tells us how strong the connection is between atoms.
Precisely. And this leads straight to the equations describing how Santa Mar changes over time. It depends on itself and, crucially, on its neighbors.
You also mentioned an energy term, E-dollars, lollars. What's that?
Ah, yes. G$ is like the baseline energy. It's the energy the electron would have if it were completely isolated on atom N, with no possibility of leaking out.
So the actual energy will be different from E-dollars because it can leak.
Exactly. The difference tells us about the motion.
Okay, so we've got these linked equations. Standard quantum procedure next. Find the states of definite energy, right? The stationary states.
Yep. States where the overall probability of finding the electron at any given atom stays constant over time, even though the underlying wave function, the amplitudes, might be shifting phase.
How do we find those? What kind of solution do we try?
We try to wave. We assume the amplitude $1 at atom n looks like a complex exponential, 1AAS in Ella. Here, $6 is just the position of atom n, and k is the wave number.
So we're testing if a smooth wave traveling along the lattice is a valid energy state.
Exactly. And when you plug that wave solution back into the time-dependent equations,
Something neat happened.
very neat, you get a direct relationship between the energy, E, and the wave number, k. This is the dispersion relation.
Okay, what does it look like?
It comes out as E equals E$ minus $2 times the cosine of k below.
Let's break that down. $2 is the baseline energy.
Right.
A is the leakage amplitude.
Yep.
K is the wave number, and B is the spacing between atoms.
You got it. E2A cos kb.
And the cosine part, that's the kicker, isn't it? Because cosine only goes between +1 and -1.
Bingo. That's the huge insight. Because cosine is bounded, the electron's possible energy, E, is also strictly bounded.
The crystal structure itself forces the electron into specific energy limits.
Precisely. It creates an energy band. The energy E must be between $T 2A1 when cosine is +1 and $2 plus 2A when cosine is -1.
So a total energy range of 4 L's.
That's the entire allowed band. Any energy outside of T PM 2A is simply impossible for an electron in a definite energy state in this perfect lattice. It's forbidden territory.
Wow, that's fundamental. And what about K, the wave number? Does it have limits too?
Well, effectively, yes. Because the lattice repeats every distance. B, wave numbers outside the range, pib to $ plus picometer, don't actually describe new physical situations.
They just look like waves already inside that range.
Essentially, yes. They correspond to the same physical state, just maybe with an overall phase shift that doesn't matter.
Eh.
So we only really need to consider K within that specific range, called the first Brillium zone. But the key is that range covers all the unique possibilities.
Okay, that makes sense. So we have these stationary states, these allowed energy bands. Now, how does an electron actually move? Like if we place it in one spot?
Ah, right. For movement, you need a wave packet. You can't use just one K value, one stationary state. You need to combine or superimpose a range of states with slightly different Ks.
Like building a localized pulse out of many continuous waves.
Exactly. And that combined packet, that localized electron presence, moves through the lattice with what we call the group velocity.
And how is that velocity determined?
It's directly linked back to that energy curve, the E versus K relationship we found. The group velocity is proportional to the slope of that curve. Steeper slope, faster movement for a given K.
So rope is like one baller bar.
That's the one. The derivative of energy with respect to wave number tells you the speed.
This feels like it's connecting back to classical ideas, but with a quantum twist. Which brings us to effective mass. Why do we need this concept?
Because the electron moving in the lattice doesn't accelerate like a free electron in space when you apply a force, say, from an electric field.
The lattice gets in the way or helps or something?
Sort of. The lattice structure itself dictates how the electron responds to force. Its acceleration isn't just force divided by its actual mass. It behaves as if it has a different mass.
The effective mass.
Right. And this effective mass isn't determined by the slope of the EK curve, but by its curvature, how quickly the slope is changing. Mathematically, it's related to the second derivative, 2ETK 2 field.
Okay, so curvature determines acceleration response, like mass does in FMA.
Precisely. And here's the wild part. Because the EK curve, that cosine function, curves differently at different points, the effective mass can change. Near the bottom of the band, it acts like a normal positive mass. But near the top.
Wait, near the top, the curve is bending downwards, right?
Exactly. Which means the effective mass can actually be negative.
Negative mass? What does that even mean?
It means if you push the electron one way, it accelerates the other way. It seems bizarre, but it's a real consequence of the band structure and crucial for understanding things like holes in semiconductors.
That's counterintuitive, but amazing. And this effective mass depends purely on the lattice properties A and B.
Entirely. It's a property of the crystal environment, not just the electron itself.
Okay, we've done all this in one dimension. How well does it carry over to a real 3D crystal?
Surprisingly well, conceptually. Instead of just tick-allers, you have a wave vector, math BFK, with components 6 akar, KSKST.
So the wave can travel in any direction.
Right. And the energy equation just gets extra cosine terms for each direction. For a simple cubic lattice, it looks like weak E 2ASB, assuming the spacing B is the same. If the tunneling amplitudes A are the same in all directions, it simplifies further.
But if the crystal isn't perfectly symmetric,
Then things get more complicated. The tunneling amplitude A might be different in different directions, and that effective mass...
depends on which way you're going.
Exactly. The electron might accelerate easily in one direction, but sluggishly in another. We then talk about an effective mass tensor, a mathematical object that captures this directional dependence.
Like the crystal has preferred directions for electron movement.
That's a good way to put it.
Okay, so far it's all been about perfect crystals. But real materials always have flaws, right? Impurities.
Always. And those imperfections are incredibly important.
Yeah.
Let's say we have one atom, maybe a position N0 that's different. Maybe its baseline energy isn't $T, but $2 plus fast.
So it's slightly off. What does that do to our nice electron wave?
Two main things. First, scattering. When the electron wave traveling through the lattice hits this different atom, it gets disrupted.
Like a rock in a stream.
Yeah, pretty much.
Hmm.
Part of the wave gets reflected backwards, and part gets transmitted forwards, but maybe with a phase shift. This scattering is the fundamental origin of electrical resistance in metals.
The impurities literally make the electrons bounce back, hindering the flow.
That's the essence of it. The more impurities, the more scattering, the higher the resistance.
Okay, that's scattering. What's the second effect? You mentioned trapping.
Right. This happens if the impurity atom is actually more attracted to the electron than the regular atoms. So if that energy difference, F, is negative.
It's like a little energy dip at that one spot.
Exactly. If that dip, that F, is negative and large enough in magnitude, something really interesting can happen. The electron can get stuck.
Stuck? How?
It forms a bound state localized right around that impurity atom. This state has a definite energy, but crucially, that energy lies below the normal energy band we talked about. EL.
Below the band. So it's in that forbidden region we discussed.
Yes, but it's only forbidden for propagating states that extend through the whole crystal. A localized trapped state can exist there.
And because its energy is too low to be in the band, it can't just wander off.
It can't easily tunnel away into the main lattice, no. The probability of finding the electron far from the impurity drops off exponentially. It's trapped in that local energy well.
It doesn't have enough energy to climb out into the states that allow travel.
That's a perfect analogy. This trapping mechanism is absolutely fundamental for how semiconductors work, creating localized states for electrons or holes. And Feynman points out this beautiful mathematical connection. The energy of these bound states corresponds exactly to places where the scattering calculation predicts an infinite reflection. The math links scattering and trapping perfectly.
So finding where scattering blows up tells you where bound states can form. That's elegant.
It really is.
Okay, let's try to wrap this up for everyone listening. We've gone from a simple line of atoms to some pretty deep concepts about solids.
We have.
So, takeaway number 1. Electron movement in crystals isn't like particles bouncing. It's a wave leaking, tunneling, quantum mechanically between atoms, driven by that amplitude A.
Right. Pure wave phenomenon.
Second, because of the lattice structure and that cosine relation, the electron's energy is confined to specific bands. It can't just have any old energy.
EPM2A4 in the simple model. The bands are key.
Third, electrons respond to forces kind of like classical particles, but with an effective mass that depends on the EK curve's curvature, not the electron's real mass. And this mass can even be negative.
Determined by the crystal, A and B. It dictates the dynamics.
And fourth, real-world imperfections matter hugely. They cause scattering, which is resistance, and if they're attractive impurities, they can trap electrons in localized bound states below the main energy band.
Scattering and trapping, the two sides of the imperfection coin.
So what's the final thought here? What's really striking about this whole picture?
For me, it's how this incredibly simple starting point, just a line of atoms with a leakage constant A, generates all this complex essential physics: conductors, insulators, semiconductors, resistance, effective mass.
It all emerges from the basic quantum rules of waves and tunneling in a periodic structure.
It really shows the power of the quantum description.
Absolutely. The lattice itself tells the electron how to behave.
Amazing stuff. Well, that's our deep dive for today. Thanks for walking us through Feynman's take on electron propagation.
My pleasure.
And thank you all for joining us. Keep digging into the physics, and we'll catch you on the next deep dive.